completed his Bachelor of Technology in majoring in Electronics and Communications Engineering (ECE) from NIT Trichy in 2011. So he then pursued an MS degree in Space Systems Engineering at ISAE Soubero. I hope I'm pronouncing it right, sir. It's from Toulouse in France, followed by a PhD degree in astronomy and astrophysics from a PSL Research University in Paris. So his research plays a crucial role in understanding the planetary interiors and evolution. It has significant implications for planetary exploration and mission planning in search for habitable worlds out there. Now, on behalf of Nakshatra and the attendees, we sincerely thank you, sir, for taking your time in your schedule, and we hope to learn a lot from you today. So, yes, sir, the spotlight is all yours.
Okay, well, thanks so much for the kind introduction. Let me put the slides up for sharing. And great, can I see that? Okay, I can see that. Okay, great. Okay, can you see my slides?
Oh, yes, that's visible.
Okay, perfect. Well, thanks so much for this invitation. You guys are all very special for me because, evidently this is an opportunity for me to give back something to the place that, really played a significant role, to say the least, in shaping my, I think, work ethics, attitude towards life, and so on and so forth. So today I'm, it's a bit of a mix, and I'll try to make it conversation. I haven't practiced the slides. I'm just going to be blunt, but I'll try to put together what I think was what was expected of me. So this was initially, the Nakshatra team reached out asking for some guidance into careers in space. Frankly, I did not plan this out to reach this career, but I had some interests, and along the way, I learned stuff, and there was a lot of learning involved, and a lot of failure involved. And so, like a scientist, I like to deconstruct things into bits of pieces so that I can fully understand them. And so that's what I've tried to attempt to do here as well. So yes, can you hear me okay?
Yes,
I just heard, okay. So forging and conventional path in space science. As the title suggests, you kind of need to forge it. Following paths is kind of overrated. It's kind of boring. But when you take control of life, control of things that you can, you need to kind of forge them, and you run into issues and roadblocks. But it's more the journey that's a lot of fun. And it comes with a caveat. This is not for everyone, mainly because the life circumstances we are all in are very different, and our needs are very different. And for me, this was essentially trying to fulfill curiosity and love for space. So I passed out of NIT Trichy back in 2011. Studied electronics and communication. The reason I got there was mainly I was actually interested in space communication engineering, but unfortunately I didn't get to learn a lot about it. And so there was like a bit of a mismatch between expectation and reality. So I wanted to really learn more about space. So that's what kind of changed my trajectory a bit there. So yeah, let's get going. So as you may have guessed, this is a question I get a lot. And like, how did you get into NASA? So it's a fair question, right? But I think it has inherently less value, um, mainly because it's I'm thinking like a scientist here. Okay, so it's focused on the outcome. Um, the answer to it is kind of rooted in the past, and there's no evidence that it may still hold, right? So it's so I'd encourage people to kind of slightly change that thinking process. And so a better question would be, um, how can I work so hard on some topic that people at companies and institutions that I want to work for approach me for problems that they are currently interested in solving. So it's very different as compared to the first question, right? And there are really several layers to this. Um, so, if you slice it up into pieces, you'll notice the shift from how did you get into NASA to how can I, do the work. So it's a shift from you to I. So there's ownership of how you want things to go to begin with. There is also like a tremendous amount of hard work involved, behind the scenes mostly. But there's also reward on the other side. You just don't know when you're going to get it. Okay, but there is a reward on the side. And it has to be some specific topic. So, you had to work hard on a very specific topic. It can't be all over the place. You have to kind of pick one. Um, Otherwise, you don't get depth. And then once you have identified that topic, you go all at it. Okay. So that's on the topic. And I try to generalize a bit here into from NASA to companies and institutions, just to because it kind of holds value across both academia and the industry. And the reason I mentioned people at companies and institutions is because institutions and companies are not real. They are just legal entities. Okay. What you want to get the interest of are people working there, which means you need network. You need to connect with people in real life, IRL, right? So you guys have to connect with those folks in order to get your work visible in some way. And then the companies that you want to work for. Why? Because then you form a deep connection. So for me, uh, I think it was initially NASA, but it's, you'd never know that's indeed that's what you're trying to aim at. But broadly for me, it was more like, hey, like all the institutions doing kind of research into space sciences across the globe, and then you kind of narrow in and you pick what you're mainly the deep connection that you want to form is so that you can forget about all the hype and rather focus on the work. Okay, so that's mainly what I intended to mention in that sentence. Then approach me, which means you have to put in a good amount of effort to kind of showcase your work once it's done. Else no one will know, right? So you kind of have to be out there, network. This could be through interviews, maybe when you get a chance, or at conferences or workshops or seminars like these as well. Just network, because that's how people will know what you're doing. When I was studying at NIDTG, there was no like Nakshatra, there was, and so kudos to folks who started it, and formed a community, because now you have people coming and presenting stuff, and that forms a network. You can better connect. So yeah, that's one of the things. The other one is then, for problems that they're currently interested in solving. So it has to be like a current interest, and the problems that they are currently interested in solving, right? So there's a time relevancy to it. You could be working on something big, but if you can't show it's relevant now or sometime in the future, it kind of gets difficult. So try to put that into a question, and this is how that would look like. Okay, so that's but many of those things aren't really in your control. You can take control, and but one of the things that I found that you can easily take control is how you think. And how you think has obviously a direct impact on the kind of work you do, what you do, what you become, and several much more things. Okay, and now I've seen many. The reason I say this is because I've seen a lot of people who are not quite happy, their entire life sometimes, because they maybe did not get into an IIT, or didn't pass the UPSC exams, or all the tough exams that we are kind of nudged to write. Yeah, so I've faced such. So essentially, you want to take control of those thoughts and work with what you have, right? So that's a slight change in mindset. For me, this was another example. Like my peers were like, hey, getting into NASA, I know that's like a dream and stuff, but you need to be a US citizen, right? That's the typical answer, but there are ways around it, right? And if not, I wouldn't be here. And rejections are another thing, right? Like you learn quite a lot from that, and it does kind of impact how you take it, how you think. Like for instance, in my case, I'm giving all personal examples, just so that I can you can relate maybe to it. For example, I was kind of rejected for all companies that I sat for interviews at NIT Trichy. Believe it or not, it was quite tough, and there was a lot of self doubt, a lot to think. But in hindsight, things are much easier to understand in hindsight. Is mainly because deep within, I kind of did not fully believe that I was good enough, and I know that I did not work on it either. Like I didn't work really hard on studies back in college. So it's a learning. It was a very valuable lesson. But the problem was, when you don't put in the hard work, folks can see it, right? So when you sit at interviews, they can see it quite easily. So there's a mindset there on how you think and how it directly impacts what you do and what you become. And so for me, for example, when I found and this opportunity to study more about like space systems in France, it felt like, yeah, this is it. This is where I'm going to fully immerse in this topic. It's related to space. Is what I want. I get to learn a bunch of stuff, and then I hit a new roadblock, which is like I was very broadly scoped. That was, I think, one of the major issues, because there's so much to learn, and you get your interest kind of broadened. Like, hey, I want to do this and that and that and that, but then like I mentioned before, you don't quite get the depth that you hope for. And the second was also engineering positions had kind of like a restriction in Europe, similar to like in the US, right? You need these ITAR clearances and things like that. But if I had thought that I could do nothing about it and just things would not have been the same. And so that's when I really thought to myself, or made that pivot from engineering to science, because I knew my foundations were quite strong. I liked physics. Math was cool, interesting. I understood stuff, and that just opened up a bunch of opportunities. And there were very less restrictions. So there was a lot of things I could work for and build my kind of repertoire to understand things that I'm interested in. But it doesn't mean that there weren't hurdles. There were. I was competing with people who had very specific degrees in that field, and my background evidently seemed very yeah, different, to say the least. Um, but again, mindset was critical there as well, because I still knew I was curious, and I tried to showcase that curiosity to folks that I met, um, like professors, scientists, and in the end, three of them, three professors, distinct institutions in France, they gave me a chance. There's also like 200 rejections. Nobody talks about that. But yeah, there were three. I still had to pick one because that was for the PhD program in the Paris Observatory, and Paris Observatory, and you can do research there. You can enjoy the view of the sea back in Nice Observatory, and so it was really fantastic. Um, I had I had I think I completed my PhD in like 3 years, and uh, I found myself literally hopping to work out of excitement because I really loved what I was doing. Um, and I could forget about everything else and just immerse myself into that work. And I think that's when I realized that when you start really doing stuff that you enjoy, um, you can't keep track of time. You don't feel time flying, and it's just you don't feel the effort. When you do things that you don't kind of like, you do feel it. um, but yeah, that's really when I had a lot of fun and a lot of learning, and that kind of shaped what I do today. Okay. Published a bunch of papers, and got some stuff working, and solved some problems which were hard. Um, uh, and evidently, as I was going deeper and deeper, you do get into a very narrow field, right? So that's one of the consequences. But it puts you in a very special spot, because if people are interested in what you do, what you know, then if they're working on that same problem, like I mentioned before, then they want you to work for them. And so that's how NASA happened to me. Um, I presented my work at a conference, and my current boss passed by, and um, it was yeah. I showed him the work that we're doing and some of the other work, which was more interesting, and it was yeah. There was a genuine connection there, because it turned out he was also a student from ISA Supero in Toulouse, when he was doing his bachelor. So yeah, we kind of connected on that, and there was an opportunity, and things happened from there. Um, so yeah, the thing is, so this was my path, right? So this was a very different path for me, and very unique to me. And I think and this is what I want to say to you all as well. Like, if you find, you will have your own paths, provided you do that work, and the way you think, how things change when you put in that work. Yeah, so the field that I entered to is called planetary geodesy, and I'll try to talk a bit about it, so that you guys can get a feel of the science that goes behind it. And feel free to interrupt if there are questions, or maybe you can take questions at the end. But if you're falling short of time, something like that. Okay, so I will talk a bit about planetary geodesy, which is it's a science of measuring like bodies, like a planetary bodies, gravity, topography, rotation. So essentially measurement, a lot of measurements involved. And specifically, since I've been mostly working on the moon, I'm going to talk about lunar geodesy. So this is so let's start with gravity field. Okay, so there was a mission called GRAIL. Stands for like Gravity Recovery and Interior Laboratory. So it's a twin spacecraft mission that's kind of for a span of about a couple of months. It went around the moon. It was a unique way of mapping out gravity field. Gravity field is essentially the way the mass is distributed on a planetary body, right? And what was unique is that previously, as single spacecrafts were going around the moon, it was kind of hard to track these spacecraft as it went behind the moon, as you see from the Earth, right? So on the far side. And so the good thing here there was inter-satellite tracking involved in addition to tracking from Earth. So that kind of enabled you to map out slight deviations in accelerations on these spacecrafts. The very nice example I'd like to give is, like, think of it like a vehicle kind of going above a speed bump. So first you'd feel the force that's felt on the front two wheels, and as it moves forward, and a similar force would be felt by the wheels behind, right, as it goes over a speed bump. So if you kind of separate out, similarly, if you kind of separate out all the known forces here, like gravitational pull on these spacecrafts acting from different sources, and you also have some non-gravitational forces acting on it as well, like radiation, pressure, etc. So what you're left with, if you model all these, and what you're left with is the gravity of the planet around which these spacecrafts are orbiting. So this technique was initially developed for the Earth to get really high, precise, and like high resolution mapping of the moon's gravity field. And so this was kind of extended to the moon. And the good thing was that it's also sensitive to like the wavelengths in which you measure the gravity field is sensitive based on the distance between the spacecraft. So they kind of vary, and also the height can make sensitivity changes. So you want to go fly very low, and arrange to get a mapping of different range of wavelength. Wavelength has in different features. Okay, features of different sizes. Then you can kind of track and map those, just because of the pull acting on these spacecrafts. So what you would end up with is something that looks like this. It's color coded. So yellow is kind of flat. Red is like the mountains where there are mass excesses. Think of like mountains. And then you have mass deficits, which are like valleys, which are more in the blue and green areas. So yeah, this is why this is so cool. It's because it's the lack of so much of mass movement around the moon as it evolved. Because think of it, the comparison is with Earth, right? So You have rivers flowing, you have oceans, you have the atmosphere. It's driving things and making changes very rapidly in terms of, when you think of geological time scales, like billions of years. But on the moon, things are uh, uh, doesn't change much because of the absence of all these elements. So what you see are like impact craters. You can see, the effect of rebounds as that impact happens. So all that central high that you see in red, and you can see the circles around it, which are like mass deficits, just because how the way uh, how impacts from different objects kind of shape or redistribute the mass on planetary body surfaces like the moon. So essentially, it gives a record into the history of impacts and the moon itself, and how it evolved over billions of years. Um, so that was gravity. Just very briefly on gravity. Similarly, we can also measure topography. So like again, mountains, valleys, but not in mass, but in terms of topography, right? How the different heights and elevations. So this is done using this amazing spacecraft called LRO, which is the Lunar Reconnaissance Orbiter. Maybe some of you know about it or heard about it. My team is heavily involved in this, and they worked on these lasers. These are called LOLA, which stands for Lunar Orbital Laser Altimeter. We like acronyms, as you can see. And so these are different spots falling on different surfaces, and then you can measure the time of flight. And there's a lot of processing involved. And you can kind of map out these. You can make digital elevation models out of these, and we have really cool stuff. The data maps of these areas available for access, for free, or for free to explore. You can, like, one of the nice. I can show you some websites later if you have time. But it's really cool stuff. And this is how it looks like. The topography, again, color coded, just to make things more pronounced. So the reds are, again, highlands. So that's like the far side, where you have like the highlands and the mountains, and the near side, they're mostly flat. And like this is the near side of the moon that we see from the Earth. And you can see it's mostly like bluish, which is greenish, and that's mostly flat plains, and that's because of all the mare regions, which are all the volcanic basins, which kind of leveled out in that area. So again, a lot of information it provides regarding volcanism and tectonics and all the stresses that act on these planets as it cools down. So that's a lot of fun stuff in there as well. And it's still collecting data. It's still going around the moon. But these models tell a good story deeper into the history of the moon. So we covered gravity field, topography. Um, let's talk about a bit about orientation. That's my kind of favorite, because very dynamic. So the moon's, I'm not talking about the moon's phases here. That's the most evident thing you see. But what I want you to focus on is, the slight wobbling motion, as the moon goes in its orbit, which is slightly eccentric, right? So there are times where it's closer, and there are times where it is slightly further apart, and there's a wobble associated to this, and that's primarily because of the eccentricity of the orbit and how the rotation has to kind of catch up to it, because of the changing speeds in the orbit. So we call this lunar librations. You have like a nodding motion in latitude that's mainly coming from inclination, but you also have like these longitude motion, which is like right east-west hemisphere kind of nodding motion that's coming from the eccentricity. So what's useful in this, right? One nice example, again, I like to show it, and let's see how it goes. So this is one of the, think about that wobbling motion, okay? Now, so this is like a fun experiment by Donald Pettit on the International Space Station, in which he kind of takes like two egg-like decoys, and one of them contain like a fluid. So I've marked A and B on the kind of end locations of these heels is going to spin them, and one of them contains a fluid, and the other one has a solid interior. So the question to you all is, which of these two contain a fluid? Okay, so I'm going to make it run a couple of times. So that's A, and the second one, that's B. Again, that's A, and that's B. So you can see the rotation is kind of slightly different. So A is very uniform, B is kind of chaotic, right? So revealing the answer is B has, it contains a fluid. That's because the solid interior, it kind of helps maintain a constant distribution of mass, and so it gives a very steady angular momentum. And so it's using this a very similar principle, but we have to code that in a equation form. You can express it as some differential equations, and you kind of have to account for all the torques acting on it and all that from the planets and the gravity field of Earth and so on and so forth. But if you do all that right, then you can predict the rotation of the moon to a very high degree of precision. So that's modeling aspect, right? So now we need some data to kind of constrain that model, and for that we use this technique called lunar laser ranging. This was an experiment that began in 1960s, late 1960s, wherein there were these reflectors. So there are two sets here. So you can look at the blue and the yellow arrows on the right. So the blue ones are from the Lunar Code missions by the then USSR. And on the yellow ones are the Apollo missions, which carried like these retro reflectors. So retro reflectors are kind of unique. They have like a very cool property, which is they're essentially like three perpendicular mirrors. And when you shine light on them, or when you look into it, you see yourself in whichever angle you're looking at it. And that's because of the way the incident and the reflected angle, they kind of go in the same direction. Okay. So why is that helpful? Is because the moon rotates, changes the direction, and so it becomes no matter what the libration of the moon, that rotation motion, you can still kind of bounce laser pulses onto it and get them back on observatory. So this is the lunar laser ranging experiment. So these are observatories which have decently large telescopes, because you need a good amount of aperture, mainly to catch photons as much as possible, because you lose a lot of photons on the way up and on the way down, just because of the divergence as it hits all these atmospheric particles, right? So and yeah, so right now there are like 5 retroreflectors on the moon's surface, and which we continue to range to them from the Earth. There are a couple of stations which are still operational. So the ones which are operational are like the Apollo station. It's in the US, it's in New Mexico. There's one in Graz, which is very close to where I did my PhD, and there is one in Germany, which is Wetzel, and in Matera, which is in Italy. And it's all kind of located in a very narrow band of latitude on the Earth. McDonald was a previous station. They're no longer operational, but and similarly also in Hawaii, in Haleakala. There's also proposed stations in South Africa, but we haven't been able to range to them from them yet. So it's an international effort, and I'm currently the principal investigator for the Goddard Lunar Data Analysis Center, which is takes care of this business for us, wherein we take range measurements from these different stations, analyze them, try to estimate positions, and inform the U.S. government on what all you can do with it and all the cool science that you can do it and disseminate it to the public. So that's my primary focus, and I can show you some nice cool pics. So this is how lunar laser ranging looks like. It's hard to see with the naked eye, the laser pulse, but over a good amount of exposure, you can see it. And this was taken during a lunar eclipse, and this was ranging to the Apollo 15 reflector. And why did we do this during this eclipse? Is because the temperatures kind of influence how the properties of these reflectors, because they're optical instruments, right? So these mirrors, when they get heated up, like temperatures, it goes from like I think the coldest it gets is like around minus 130 or so Celsius near the equator. And when it's in the shadow region, then it's when that's when in the shadow region, and when it's daytime temperatures are like 120 Celsius or so. So you can see, the thermal effects kind of acting on these reflectors, and so it kind of becomes difficult to range because these temperature affects your gradients of the refractive index, right? So it kind of doesn't give you back the photon in the same direction as you fire. So you don't get ranging observations during that time. So eclipse was a very cool opportunity because you have the moon comes in the Earth's shadow, and so it gives that time for it to cool off, and so you can perform range observations during the full moon, so to say, at least in that Earth Moon configuration. So yeah, that's some cool data that was collected from the Apache Point Observatory in New Mexico. By Tom Murphy was a co-I on that, and now that facility is now operated at Goddard, by Goddard, I must say. Okay, so yeah, so how well can we measure those reflectors? The range itself from the reflectors, we can get them really precise, down to few millimeters, and that has really enabled us to dig deeper into questions related to the moon's interior structure, just because how it's sensitive to the rotation, like the decoy that I showed you. And there's a lot of fundamental physics as well tests that you can do. I published a paper on that back in 2017 on it's essentially the equivalence principle. It's like dropping like a hammer or a feather on the surface of the moon. Both of the materials have to kind of fall down at the same time, right? So similarly, we are setting up that experiment in the gravitational field of the sun, the Earth, and the moon. So we're testing out the moon and the moon and the Earth as test particles, just like and seeing the rate at which both of them are kind of falling in the gravity field of the sun. So that's and the test holds true, obviously, as we know it. But our aim was to mainly test at what level that principle holds true, and see deviations from it at the level of our measurements. So that's a way you test theories of general relativity, for example. So 7 millimeters, we did not get there easily. It was back in 60s, it was like meter level, and then it came down to a couple of centimeter level, thanks to like new lasers technology and those kind of things. Detectors were good, timing instruments. There's a lot of things that goes behind those observatories, and they're doing a lot of hard work. These are a lot of engineers, optical engineers who work on this to collect the data, get them as precise as possible. And that's part of geodesy as well, right? Because you're collecting very useful data, which can be analyzed by like scientists to explain some of these physical phenomena. So we're not happy with 7 millimeters. It's we want to get better. And so latest news. So we are so the team at University of Maryland, some of my collaborators are involved in this. We are going to place a new reflector, and this one's going to be different. It's not going to be like an array that you saw earlier, but this is going to be like a single corner cube, like a big fat corner cube, 10 centimeters or so in diameter. And this is on the Blue Ghost mission, which is kind of scheduled to land on March 2nd, I think. I'm not sure about the times or time zones, but we are hoping that this lands and we get back photons, and so all that activities is in process. We're trying to estimate and see how we can track down the positions of these down to just so that we know where the lander has landed. It's mounted on, I think, the like patch antenna, which is used to communicate with the Earth. So it's kind of cool because you can then orient it to, if all goes well, let's hope it goes, we can then orient it towards the Earth, and then we can shine lasers on it and get measurements and make these tests and continue this research into the future. And this data would be out there into the public, and so that the next generation, that's what it stands for. NG stands for next generation laser ranging retroreflector. So we expect that it's capable of getting much higher accuracy on the range measurements to this. But there's a lot of pieces involved to get to that good level of accuracy. So you have to improve all those systems along the way to hit that. But I think it definitely enables it. So you guys, you have to work on this and then improve the systems and continue research into the future. Now, some cool stuff. So this was one of the things, and it's all in the public. So I'm not sharing something which should not be shared. Or how is this valuable? So as valuable as it can get. Look who's interested. It's the United Nations. So I got the opportunity to attend this workshop, although not in person because of some travel restrictions. It was a lot of discussion on what can enable position, navigation, and timing. The standards involved for the future, and one of the key elements of the workshop is also on the reflectors play a major role in kind of the positioning aspect, right? Because you want to be able to define reference frames, which are you want to have very highly accurate reference frames, so because it's essentially getting to decide what zero longitude would look like. You can define it, but the process behind is called realization of the reference frame, where you have to kind of estimate the position of these reflectors to say that, hey, this is that specific lat lon or XYZ, and then we need to kind of define the rest grid based on that. So there's a lot of work that goes into that, and analyzing laser ranging, it enables that definition of reference frame. So the more higher quality of measurements we get, the better reference frame you can have. Think of it like on Earth when you have the GPS. We have these GPS receivers, and you kind of don't know the position of that really well just because the grid is not good enough. So it becomes a problem, and it kind of limits what accuracy you can get on the positions as well, because your base is kind of not enough accuracy involved. So so this is there's a lot of work that goes behind that. Today I will refrain from talking about timing aspect, but there's as I'm sure you guys must have seen Interstellar, time doesn't tick quite the same when gravity changes, right? So a clock that's on the moon would tick at a different speed as compared to a clock ticking on the Earth, mainly because of the changes in gravitational potential, and because how that kind of changes space-time as we know it. But yeah, there's we are trying to help define standards for that, and there's a lot of work going into that to define what time should be on the moon. Well, we're not going to have time zones, but we're going to have standards in place like the UTC to be able to track time with respect to Earth, because most of us are on Earth, right? So that's PNT, an application of that, and that's just a very recent Twitter update by Firefly, which is like the company that's going to take that retroreflector and put it on that red spot that you see on the right, which is kind of a lava floodplain, which is called the Mare Crisium. It's the value that it adds because it's closer to the limb of the moon as we see from Earth. So when you range to those, you kind of get a very good sensitivity to those librations that you saw before in longitude. And that's where most of the model errors are. So we want to improve that. When we get more data, we want to also add a new spot on the moon, which we can track in order to enable like the reference frame realizations and such. So yeah, stay tuned for updates on that on all socials, and there will be a NASA coverage as well, I think. So yeah, with that, I think I'm happy to take questions, and we can discuss for maybe like 15 minutes or 20.
Yes, sir. Now we are open to questions. So, one question?
Sir, am I audible?
Yes, I can hear you. State your name and department, which year, so that.
I am Sandeep from third year instrumentation and control engineering. I'm the technical head in this club. So, my question is pretty simple, sir. Like, retroreflectors were placed on the moon's surface in 1969 during the Apollo mission. So, won't the reflectors be damaged by now because of all the dust and all the impacts?
Yeah, so that's a good question, and it's the thing is, it's we are still able to range to them, right? So something's working, which means if you're able to get ranges to them, which means the amount of dust on it is probably not as much as we think. it's all questions, right? So we can't go there and check if there's dust, right? So what we get back is data, and on that data, based on that data, we can say things. We may be wrong on the estimates, but we can get a good confidence on how much we are wrong or how much we are right. And so in terms of photons, we do get a fair share of photons back, which tells us that dust is minimal. But yes, it's a dusty environment. If for instance, if there is if there was a kind of an impact, even micrometeorites, right, coming close to it, then it would, especially low gravity environment, all that material is going to be like splashing through, and you can have a nice layer of dust near it. And there's also radiations, and there's some level of dust transportation, as you may have read, but it isn't sufficient enough, looks like, from the data to cover it. And there are some papers on it, on dust depositions. There are different groups saying that, hey, there's this much dust, and there's other groups saying that, well, we don't think there's this much dust. So we're trying out different ways to test it. So yeah, there's no definite answer, but the instruments are continuing to work even after like 5 decades. So that's phenomenal.
And my next question is, as part of the NGLR, does NASA plan to have transponders instead of retroreflectors? Because transponders will anyway give a better signal.
Yeah, that's a good question. Transponders are cool, but these are passive instruments, right? So for transponders, you need power, and power is it's a resource, and which means if it's a resource, it can be utilized, and it will only probably last till the lifetime of the mission. So when they make these choices, like you mentioned, like, why can't we do this? Why instead of this? There's a decision process that goes through that, and it's called the science traceability matrix. Okay, it's essentially how you can track what are your science objectives, what are the things that you need to achieve it, to what level do you need to achieve it, and how do you enable it, like how do you make it work. And so the thing is, we need these tracking instruments to last. Well, retroreflectors have shown us that it works for 5 decades. So it's more heavy on that side, right? So that's a very good argument that you're going to get a very good amount of timeline, like the baseline of how much ranging you can do to these experiments.
So can we use solar cells?
I'm sorry?
Solar cells.
Solar cells, yeah, you can use them, but I think they also tend to have a lifetime, and I would say that just make one radio beacon, go to conferences, okay, show it, just like I was telling you in the beginning, show it, make your case for it, and I think that's what you're trying to do here. Make your case for it, take questions, don't take it personally, take questions, try to understand what's the engineering issue involved, and then build stuff, and then you will see that people will get interested in it.
Sir, how would you?
Did I answer that question?
Yes, sir. Yes, sir. Sir, what advice would you give to Indian students who would like to pursue a career in NASA, like after masters in India?
Can you repeat that question? I didn't quite
Yes, sir.
catch
So,
the.
like I want to pursue my masters
Okay.
in India in aerospace.
Oh, okay.
So I was considering a career in NASA, but after a lot of discussions and because of funding, I decided to do my master's in India and then try pursuing a career in NASA. So how would how can I go about the process? What is the
I
process
have no
of?
idea. I have no idea, to be honest. Right? So, I mean, like I can tell you stuff based on my experience, but uh, I have not worked in India, unfortunately. Um, but I know that there's a lot of good work happening in different places. I would say, yeah, look up research institutions that which are doing work specific to what you're interested in, and take it from there and meet people and see what works. Because it's things are evolving, right? So it's not, and my advice would be outdated anyways because I have no idea what's going on in terms of yeah. So I think you know um, look at what's happening right now, and I think you guys must be much more updated than I am on that, because I haven't been following what's the new research, or who is doing what, or which institution is doing what in India, just because I'm so busy with my own work here. So
And give the mic to someone else who has some questions.
was that all
Hello,
the
sir.
questions? All the questions was from the same person?
Yes.
Okay.
So, hello, sir. This is Ankur. We final year mechanical engineer. So, I was the one who had contacted you on behalf of Harish, the president. So, yeah, even I have a simple question regarding the lunar retroreflectors. So, let's say if we point a laser at them, let's say a very high powered laser, like usually the ones you use in observatories, there's a very low chance that we might receive lunar laser signal back towards us. So why is that happening? Since the retro reflectors are like very highly polished surface, and we should be receiving some signals, right? So why is that the case? That yeah,
Well,
if
the
we
thing the
direct.
thing is the atmosphere is involved. So what happens is the pulse energy kind of gets distributed. But let's say theoretically you build a laser with like really high power, which doesn't exist right now, much more higher, much more powerful. Um, then yes, you would get back more photons, just because you're sending more photons. Kind of brute forcing. If you brute force that problem, then it works. But I think right now um, like the highest power lasers that you can get um, have like a maybe a technological limitation to it, I think.
So like,
And I
is
may
it
be wrong.
the yeah. So is it like the limitation of the laser we have here on Earth, or is it like the reflecting capability of the retroreflectors?
It's all on the pulse that you send. You get what you send. You get a fraction of what you send. The reflecting capability, it stays the same, right? Because it's a passive device. It's like a mirror. It hits back, unless there's some heating going on or the environment changes there are affected. But otherwise, it's yeah.
So basically, that means that the higher power laser you send, the larger fraction you receive here, larger fraction
Yeah,
of that pulse. Okay.
yeah.
So yeah. So a second question would be like, since you had seen like both, you had done your education in the US and education in the Europe, and then currently working in the US. So like, was there any particular reason or motivation behind this? Why didn't you could have worked in European space agency? So why did you decide to move to US after your masters and PhD?
I think it was um, yeah, it's a good question. I mean, there's typically the advice that you'd get after you do a PhD is don't stay in the same place for too long. Okay. And why? It's because you stagnate, because the rate at which you exchange ideas kind of drops, because you become comfortable, you become familiar. You're not hearing more new things, or you're not participating in more stuff, just purely based on familiarity and what's going on in that area. So there's the typical advice that you get is move to a different lab, different country, different continent. And so, yeah, that was the advice I got. And I kind of valued it because it was coming from somebody who had done that in the, several generations ago. So it was good advice in the end, because it opened up more opportunities, more growth aspects, career, mainly career-wise. It was a very good jump for me, and thought it was a good time. And they don't come by that easily, right? So it's all the more incentive.
Thank you, sir, for answering those questions.
Welcome.
Hello, sir. Good evening. This is Harish. So I have a fairly technical question to ask you. So the laser frequency that you're going to use is 1064 nanometers, if I'm not wrong. So are you worried about any sort of frequency instability or like instability in the frequency of laser? Because if you're only focused on getting the light back from the reflectors on the board, are you worried about the frequency instability, or like if you are you using any sort of optical cavities to stabilize that?
So, I mean, the wavelength choice is mainly based on how efficient it is, to run, how stable it is over time, those kind of things. So I think, like previously, I mean, over generations, that wavelength has changed. So it's been, I think, something in the 600 nanometer was initially in 1960s or so, and then it came to 532 nanometers, just like the green spectrum, and that stayed for long, because there was a lot of good lasers developed at that time. And more recently, we switched. Well, I wouldn't say we switched, but like so, like the French station Grasse, and I believe Betzel as well. They switched to infrared, mainly because availability is one thing, but the operations was much more favored in infrared, because the based on your wavelength, there's a dependency on how your atmosphere kind of absorbs photons. So you want to operate in uh, frequencies or wavelengths where you have minimal absorption or very good transparency of the atmosphere, so to say. Just because we want to just push more photons up, and that's a technical difficulty there. Yeah, so 1064 is used for that reason, because infrared is more transparent, for these lasers to push through the photons through the atmosphere layers. Yeah.
Does the audience have any questions? if no one has any questions, then we will end these sessions. Yeah.
Oh, any questions for the people from the chat here?
Well, if you have questions, you can find me online. I have a website, drvishnu.com. You can go there. You can there's a contact form, or I think you can also find my email online. And I'd try my best to get back to you.
Awesome.
Does
Okay.
anyone really have any question, or shall we end the session? I think Satish from the video is trying to talk. No.
Okay.
You can answer.
So I hope everyone captured a lot of content from this lecture. I indeed learned a lot from you, sir. So thank you everyone for joining us. Thank you for the questions asked as well. And this lecture of yours was extremely engaging for us. It was very insightful, and the talk about planetary geodesy, forging unconventional paths in life is exactly what we're looking for. So thank you so much, sir. Thanks for being here. We won't take much of your time. We'll wrap it up soon. And we look forward to staying connected with you, sir. We're hopeful in hearing updates on your projects, and we would love to have a chance to work with you maybe in the future. And yes, sir, stay connected. We hopefully will meet you soon. Yes, once again, on behalf of Nakshatra, thank you everybody for joining us in the session today. And that's a wrap. Yes, thank you.
Thank
Have a
you.
great
Thanks so
day.
much. Yeah. Thank you. Bye-bye.
Thank you,
Yeah.
sir.
That was a lot of fun. Thanks. Bye.
Thank you, sir.